Okay, hello to the online folks, and my apologies for the delay as we sorted out some technical difficulties. We were just discussing the final project a little bit, and in case you're online, most of you have gotten some feedback on your introductions, but my main recurring comment was just trying to make your presentation digestible in a poster format, using bullet points and a minimum amount of information required to communicate what you're doing, why you're doing it, and how you're doing it, including which data set you're using. And those comments will go across all of the different sections that you're presenting, trying to make your presentation simple, concise, and just enough information to, so in your methods, just enough information to convey what you did. In your results, just enough information to convey what you found. And in your discussion, more bullet points, just summarizing your and interpreting your results. And there's a question here, I think, about how to present an association between two categorical variables.
Yeah, I guess I was just thinking, like you were saying about SPSS outputs aren't always so visually appealing.
Right.
So let's say you're doing across tabs of let's say age by some condition, like age of people, and the percentage within that group who have some health condition, let's say heart disease or whatever. So like in SPSS, you can do like a cross tabs that shows you, 8% of the 25 to 29-year-olds have it, 30% of the 40 to 65-year-olds have it. So that comes out like in that crosstabs table, and I was just trying to figure out how to convert that into some kind of either like a bar chart or something that's like a nicer, aesthetically and just visually is clearer. So I was using like the chart builder in SPSS, but I must not have done it. And then on the x-axis, then you can put things on the x-axis and y-axis. But anyways, I didn't do it right. So
for two categorical variables, a bar chart can be nice. The best, I would consider that as secondary to the most important result, which would be a table of odds ratios and ideally confidence intervals and p-values on those odds ratios as well.
Even if it's like a simple distribution, like a descriptive epidemiology kind of thing, like you want to know what the current, because it's a snapshot in time. Because I'm using the community health survey.
So for your descriptives, you would only put prevalences. So if it's if it is prevalence of males and females, you would put sex, males, females, with numbers and proportions for each of them, and that's enough. And I wouldn't put a bar chart for that. That's the so-called epidemiological table 1, where you're just describing your data set with with one-way contingency tables, essentially for each of the variables that you're using, and often for some of your sociodemographic variables as well. It's just where you describe your cohort, and just putting prevalences in as percentages and counts there is enough. So if you have a binary variable, you can put you could have one row, and then a common format is then actually to have one merged row, and then each level of your categorical variable as another row kind of within that variable. So you have sex, you have male, female, and for each of those you have your proportions and your counts.
Okay, so you would leave that in like the SPSS output?
Not as the SPSS output, because it's
too much.
Hard to read. Yeah, it has a whole bunch of stuff. I would take the key parts of it and put it into a nicely formatted table. I think in the assignment I put a link to a suggestion for reporting descriptive statistics that has an example of that epidemiological table 1.
Okay, but not a bar chart.
But not a bar chart. No, table 1 is better than a bar chart for your descriptives. I mean, I'm not going to dock you for putting in bar charts, but it's also not a standard way of presenting your descriptives.
So it's called epidemiological table 1. Like if I do like a Google image search, like this will come up.
Probably, but look at your assignment before you do a Google image search. I'm not sure what a Google image search will return. Yeah, it's a very, I mean, there are several different formats for it, but it is a very common thing that table 1 in your paper has these frequencies. And yeah, I don't know if it's in there, but well, I don't know if there are templates with the Word document thing. I've only ever started it from scratch, but you could also do it in Excel to make it a little bit easier. I've seen people do it in Excel as well. Any other questions? Yeah.
So how do we provide descriptors to cumulative time series data?
Good question. How do you provide descriptives for cumulative time series data? You could provide a country by country, like 1 row per country, and you have the total number of deaths in each country over the entire duration, and you also have the population. So that could be enough of a description country by country, I think.
So it's not a compulsion to give descriptors through SPSS. We can use Excel or anything else.
Yeah, you don't have to use SPSS. No. No, I mean, the point of the descriptives is to provide a very quick look that summarizes what your data set is, so someone can understand what kind of variables you have, you know, whether they're count or categorical, and understand what the numbers are. So they should be able to picture in their head what your data set looks like just from a nice little summary. In the case of your count data, you could use a bar plot for that shows the population of each country and the number of deaths. That would also work. You'll find that we're not very particular about these things as long as you manage to communicate. Everyone has different ways of doing it, and if it's clear, you'll get full grades for it. So, you know, we're not going to say, oh, you did a table instead of a bar chart. You're taking off grades for that. But if you look at it and we find it hard to tell from that what your data set was, then you might lose some points. It's just the important thing is that it's clear. So yeah, for the Ebola data set, I think either country by country table or a bar chart, just showing the overall amounts, either of those would be okay. Yes?
Like the analytical statistics section, or like the next statistics section, or there was like, so is using a data set like the community health survey? I'm just wondering, because that's like, that whole data set is just a snapshot in time. So in terms of like, you could hypothesize associations between variables, but you know, there's no, like you don't even know the direction of the association, like which one came first, like temporal order. So is that okay for this project? Like, so we can still make some kind of hypothesis or something like that, and that data set is enough for this project?
Well, I would be aware that you're not going to be able to infer causality from your analysis. You're looking for associations and you're going to report on associations, but you're not going to make causal conclusions about whether, you know, whether, I don't know, insurance status affects whether or not you get the flu shot, or sex affects whether you get the flu shot. Just associations. It's as you said, it's a snapshot data set. you're also not making any attempt to control for confounding factors because you haven't learned how to do that yet. So just be clear that this is about correlation and not causation.
And that would be okay for the section. Okay.
Yeah, I mean, you certainly will not be at all alone trying to use a cross-sectional data set to look for associations between exposures and outcomes. It's a pretty common thing in epidemiology, whatever you think of the validity of it. And there's plenty of argument over the validity of doing that. But I think for now, it's an exercise in doing a basic analysis using a cross-sectional data set, being aware of some of the limitations of what you're doing. Limitations being you cannot infer causality, you're not even attempting to control for confounders, yeah, you have really no way to determine causality. And also because the sample size is quite large, what I found in the community health survey data set is that if you pick any two variables at random, you find a significant p-value. Like really almost any two variables in the whole data set are correlated to each other. So yeah, you definitely don't want to get too excited and infer causality from the associations in this data set. Just check, are there any questions from online? Let's see. Actually, I can do that here. Questions online. Okay, Kelly, so I will monitor. Are there any questions about the assignment? If not, I'm going to go ahead and get started with our lecture. And I am watching for questions coming from the online audience. So we're going to cover today correlation and regression, which you will use for situations of two continuous or discrete variables. By the end of today, you should be able to identify simple linear regression, the assumptions required when it is used, and also define and calculate Pearson's correlation and coefficient of determination, which are related to linear regression, and define residuals and sum of squares, which are used in the calculation of linear regression and Pearson's correlation results. And all of this is from chapter 7 of your textbook. Just a sec, there was a question, Kelly, do we need to formulate a hypothesis for the project? Yes, I would recommend that you state a hypothesis in your introduction. It is a good way to define the motivation for your study. So because from simply one statement of hypothesis, someone looking at your introduction will know something about what your motivation for the project was, what kind of analyses you might have done. It is it's just a useful thing to help orient someone new to your study. Another question, in the Ebola data set, mean, median, standard deviation do not make sense as the data are cumulative. So is it okay if we do not show mean and standard deviation? So I assume you're talking about in your descriptive statistics, in which case, yes, it does not make sense to give the mean and standard deviation of number of deaths as they accumulated over time. I think sufficient descriptive statistics, as I mentioned earlier, would be just the total population of a country and the total number of deaths, and perhaps the length of time that country was observed. That would be fine. Just to summarize the variables that you're using in a way that makes sense for them, and I leave that to you to decide what makes sense as a concise summary of your data. And if you're not sure, then yes, please ask. But yes, that's a good point, that mean, median, and standard deviation don't make sense for a time series. Okay, so we've done a number of procedures for inference on 2 variables, although so far none of them have been for 2 continuous variables. But in each of these cases, we have, in the cases of 1 continuous variable, such as analysis of variance, we have thought of the 2 variables. One of them is the response or outcome variable, and the other one is the independent or the predictor variable. And we often think of them this way, relating to our hypothesis, and even when causality is unknown, because regression procedures are formulated in this way, with an X variable, the predictor, and a Y variable, the response. And inference is performed for association between that predictor and the response variable. So for 2 categorical variables, we didn't actually have a predictor and a response. We just had a 2x2 contingency table. It made no difference which one was the predictor. We calculated the chi-squared value just based on differences between the observed and expected values for each cell of the table, and that was a test statistic that always increased with greater dependence between the variables and greater differences between the observed and expected values. So the chi-squared could be calculated for any contingency table, but risk ratios and odds ratios could only be calculated for 2x2 tables. And when you calculate odds ratios and risk ratios, you do think of a dependent and an independent variable. The independent variable, or the predictor, would be the one going into the ratio that you're calculating, and that would be the effect of the predictor variable on your response variable. So when we had a continuous response and a categorical predictor, we could use the t-test and analysis of variance when there is a categorical predictor. And for descriptive statistics, we have the box plot, we have the bar plot. So when both the predictor and the response are continuous, we're going to introduce regression and correlation. And our workhorse descriptive plot here is the scatter plot. So this is something very commonly used in the literature. I just typed into PubMed Pearson correlation and saw many thousands of results, and I just pasted in the first few abstracts. So this is from anything in PubMed. Let's see, this first one that came up relating to some things that I know nothing about. Glutathione-mediated detoxification of something, drinking water disinfection, byproducts in T24 cells. So at least I can tell enough that they're looking at byproducts of drinking water disinfection on T24 cells, which are immune cells. And I don't know what any of this stuff really means, but I do see down here at the bottom, Pearson correlation analysis showed that the cellular GSH level, so this is one of the byproducts, is inversely correlated with ROS production and cellular GST activity in HPQ-treated cells. So they are avoiding any causal language here. They're just saying that the amount of this byproduct is inversely correlated with several of these measurements of cellular activity in the T24 cells. So inversely correlated, that means that when the predictor goes up, the response goes down. And this, by the way, is a form of, so this is, they're not, well, this is a result of a hypothesis test. So they're saying if you have a null hypothesis of zero correlation, they have rejected that hypothesis and are saying that there is an inverse correlation. Let's see, another one here, validation of the quality of life threatening illness family care aversion in German-speaking carers of advanced cancer patients. Okay, so this is some kind of a score, a quality of life score, and validation of it for cares of cancer patients. And looking past everything, I see it is about palliative care, and the objective is to translate and validate this this index in a certain cohort. And they are validating it by looking at Pearson correlation between test and retest. So just subsequent tests to determine this score, and they have a correlation of R equals 0.92. We'll find out later what that means, but that's pretty good because the best that you could get here is 1. And as expected, a significant positive correlation was found with hope, R equals 0.4, so this quality of life score is positively correlated with hope, and negatively correlated with traumatic stress, depression, anxiety, and overall subjective burden. So this is kind of a nice example in that you can imagine that, never minding data or the study or anything, that a quality of life score should be positively correlated with hope and should be negative correlated with these other things. So it's a quantitative measurement of this thing that kind of makes sense intuitively. Last one, folic acid supplementation on homocysteine levels in children taking anti-epileptic drugs, a randomized controlled trial. So here's one where we can make causal conclusions, even without adjusting for confounding or anything, because there's been an experimental randomized intervention. So materials and methods, correlation was tested by Pearson correlation test and p-values. Okay, but what correlations? So they did both a chi-squared test, unpaired t-tests, and correlation. They did a lot of different tests here. The reduction of THCY in the experimental group was 1.92 micromoles per liter, and in the control group there was an increase. Okay, so that's something that they did by t-test. I don't see where their actual conclusions relating to correlation are here. But they used it. Okay. let's look at the relationship between scatter plots and correlation. Scatter plots being these dot plots with an X and a Y axis, and correlation being a measurement of the strength of correlation that we see between two variables. So keeping in mind this, correlation will be a description of the linear relationship, not any nonlinear relationships between the variables, and it does not imply causal effect. It just means when one goes up, the other one tends to go up, or when one goes up, the other one tends to go down. What do I mean by linear relationships? Here's a couple examples on the left. This is a weak-ish linear relationship. Positive or negative? Positive. Another linear relationship on the bottom left. Negative. Yep. And a couple nonlinear relationships.
Those are relationships, though.
It is a relationship.
It's like a parabola relationship, or
This
whatever.
is a parabolic relationship. Exactly. This is not a relationship that we can describe using correlation.
It's also like it's not random.
It's not random, no. It's just not linear.
Are there, just out of curiosity, are there like methods for describing those kinds of relationships statistically?
There are methods. The simplest method in this case would be a polynomial regression, where you consider it would be a multiple regression where X is a predictor, but also X squared is a predictor, and that would help you identify this parabolic relationship. There are also generic measures of association that tend to involve creating bins, so categorizing these variables. You don't do much of that in epidemiology, and probably won't cover those methods in this program, but the polynomial regression, you will cover your next couple of biostat classes. Here's another one that kind of looks like a parabolic relationship. This, you might have some linear and some nonlinear relationship, or maybe it's all nonlinear. You can't really tell from just this. So correlation is going to capture not only the direction of linear relationships, also it will somehow reflect the strength of the relationship. And when I say strong relationships, I mean cases like this on the left, where if you look at the total variability of Y, you see that quite a lot of it is explained or associated with variability in X, whether it's a positive or a negative correlation. On the right, these, assuming that the scales are the same here, there's about the same amount of variability in Y, but it looks like not as much of it is related to variation in X. Still some of it, but not as much. These are a couple examples of what no relationship looks like. So this is no linear relationship, no relationship at all. It could look like this, where the scale on the X and the Y are equal, or the scales can be different, but still the variability in Y is not at all explained by variability in X. And I just, in one more example here, what I'm talking about, this variability in Y given variability in X is drawn out a little bit more here in this plot of diphtheria, polio, and tetanus immunization versus under 5 mortality in about 20 different countries. And if we plot this, we see, so if you just look at the under 5 mortality, you see variation between 7, I assume this is per 100,000, and 208. So that's in Finland to 208 per 100,000 in Ethiopia. And you see that variability here in the scatter plot, but you see that using DPT immunization on the x-axis, that does account for a certain amount, but not all of this variability. The 2 dashed lines that I'm drawing here, one is just the mean of x. So if we were to calculate a so-called residual on each of these data points, it would be the difference from each point to this dotted line. So this is just the overall mean of y, and the residuals there are the vertical distances of each data point from that dashed line that is the mean of y. This second line, do you all remember conditional probabilities? Who can tell me something about conditional probability? One thing, anything.
The Venn diagram?
What's that?
The Venn diagrams are.
Yeah, you can use Venn diagrams to represent conditional probabilities, at least for 2 events. So what is this mean of y given x? What does that mean? That's a conditional probability that's given.
X already happened.
Sorry?
Like one event already occurred.
One event's already occurred, yeah. So this means the mean of x given that the mean of y given x has already occurred. Or in this instance, it means what is our expected under 5 mortality rate given a certain percentage of infants who have been immunized. And so this line is telling us that expected value of y changes for different x. And if you were to calculate these residuals, you would find that for the most part, they're smaller than the residuals to the dashed line. At some point, we will talk about this being a null model or an intercept only model, and this being a linear regression model. So this would be if you fit an intercept but no slope, and this line is if you fit an intercept plus a slope to this linear regression. So when I say Pearson correlation coefficient, I may be referring to the population or to the sample, just like all of the parameters and statistics that you have learned this semester. And again, when it's referring to the population, you use a Greek letter. When it's referring to the sample, you use a Roman alphabetic letter. And as usual, rho would be calculated from the entire population, and R would be calculated just from the limited random sample that we take. And this would be a test statistic. Also, by the way, sometimes called the product moment correlation coefficient. Usually you'll hear it called Pearson's correlation coefficient. This is quite a bit less common, but occasionally you'll see it called that. Is what they are. The mean or the population correlation coefficient is calculated from the population mean, standard deviation, and each of the individual values in the population. So whereas we've learned formulas for calculating the population mean. That also involved, that was summing up all the values and dividing by n. the standard deviation was the difference between each value and the mean and divided by n. And this just adds to those and uses two variables. So you need the mean and the standard deviation for each of your two different variables, and the x and the y values for each members of the population. And the sample correlation coefficient is almost the same, but as with the other, with our calculations of the standard deviation, it's divided by n-1. So that's because the mean is xi minus x bar over n-1. Just to give you a bit of intuition about what these mean, here are some examples. Here's a perfect negative correlation, an R of -1, meaning the residuals are 0, the variation in Y is perfectly explained by changes in X. And when X goes up, Y goes down, it's negative. An R of -0.6 looks like that much variability, so not all of the variation in Y is explained by variation in X. But more than here, where none of the variation in Y is explained by variation in X. And then on the positive correlation side, here's a Pearson's correlation of 0.3 and a gain of 1. So in general, if the closer your R value is to plus or minus 1, the less variation there is from the linear regression line. The smaller those residuals are, and the better Y is described by X. A few things to remember about the population and the sample. Correlations are, one, it is unit free. So regardless of whether we're talking about moles, micrograms per milliliter, or years, or kilograms, or anything else, it's always between -1 and 1, regardless of the units. And by the way, if you take your data and convert it between kilograms and pounds and grams, or make any of those kinds of unit conversions, it has no effect on rho or R. So the closer to -1, the stronger the negative relationship, the linear component of the negative relationship is, and the closer to 1, the stronger the positive linear relationship. And if it's close to 0, it means there's very little linear relationship at all. So keep in mind that unless your population correlation coefficient is exactly 1 or -1, a high correlation does not necessarily mean that it's a linear relationship. There was an example that I showed before with a slightly curved relationship that would have given a very high correlation coefficient. So even if it is a perfectly quadratic relationship, you might see a high value of R, because a fair bit of that correlation or of that relationship could be described as a linear relationship. So it does not mean that it's a linear relationship if you see even a fairly large positive or negative correlation.
Can you say though that it does imply still like a dose response relationship type of thing? Like as X increases, like there's a higher response from Y?
It does mean that for higher values of X, there tend to be higher values of Y. That's a positive correlation. Yes, that's right. And it quantifies the amount of that relationship that could be described using a linear model. So in this bottom right example here, this, even if this is not a linear relationship, you would see a fairly high Pearson correlation here. I would guess this looks like a Pearson correlation of 0.8 or 0.85 or something like that. Whereas this would be something closer to 0, the Pearson correlation. And one final cautionary note is that just as with means and standard deviations, R is sensitive to outliers. It can be dominated by a single outlier. So if you're going to report on the correlation, it is also good to take a look at a scatter plot and see if it is being dominated by an outlier. We can perform inference on the population correlation coefficient with a null hypothesis that the correlation is equal to 0. There's no linear relationship between these two variables, and an alternative hypothesis that some correlation exists, that rho is non-zero. And these are actually pretty easy to do. You can calculate R, as we showed a couple of slides ago, and using just R and N, your number of observations, you calculate this value, and it turns out to be T distributed with n-2 degrees of freedom. And you all know what to do from there, right? So even if you don't have a full data set, if you look at one of those papers where they recorded a Pearson correlation coefficient, and they tell you how big their data set is, but they didn't report a p-value, you could calculate a p-value yourself for it, even if you don't have the original data set, so you have nothing to plug into SPSS or Excel. Using this formula, you can calculate a p-value for this null hypothesis. All you need is R and the sample size, which is a nice thing to note. Try to remember that, because you will sometimes see correlations reported without p-values. So you might be interested in calculating that p-value. Let's introduce regression analysis, and this is the start of something you're going to be doing a lot of over the next year in biostatistics 1 and 2 and in your EPI. And this is just the start of simple linear regression, but there are all sorts of extensions that will build on this. The couple main reasons to do regression analysis. One is for predictions, to make predictions of your response variable or your dependent variable based on the value of your predictor variables. So that falls under the general area of what we call prediction. And the second one, to explain the impact of changes in an independent variable on the dependent variable. This falls under the category of what we call inference. And in epidemiology, it's often causal inference, that we actually want to do a statistical hypothesis test and make a claim based on that there's a causal relationship between the independent variable and the dependent variable. So if you were to put a label by each of these, the first one would be prediction, the second one would be inference. Both of these are valid and important goals under different circumstances. The dominant motivation in epidemiology tends to be the second one, inference, and trying to explain the impact of changes of an exposure on a health outcome, rather than actually predicting what the health outcome is. There are, of course, exceptions, things like the Framingham Heart Score, where your goal actually is to predict an individual's risk of heart disease. But but in most cases it is to make an inference about the impact of some exposure variable on your health outcome. Simple linear regression is when there's only one independent variable. Multiple linear regression is where you have more than one independent variable. And in simple linear regression, the relationship between our predictor and our response is described by the slope, the intercept, and a random error term. And I'll write out this formula in a little bit. Using the terminology uppercase x and y for random variables and lowercase x and y with subscripts for individual observations of that random variable. So capital X might be the weight of individuals in New York City. It's a random variable. X sub I would be individual weights of study participants who we put on a scale and weigh. So here is a formal description of simple linear regression as a description of the relationship between an independent variable and a dependent variable in the population. It is y equals an intercept beta 0 plus a slope beta 1 times our independent variable plus a random error component. And a more compact version of this alpha plus beta, same thing, just different letters. But the second one is a little bit different, and this is describing just the so-called systematic component of this model. And it's saying that the mean value of y given any value of x is described as your intercept plus your slope times x. This mu y conditional on x is also called the expected value of y, and it is sometimes instead written as, try to write this as the expectation value of y given x equals. All of these are representations of the same thing. That was a population, a model of the population where beta 0 and beta 1 are coefficients, population parameters that we might want to make inference on. We will estimate a regression model from a sample, and I'm describing this here using a hat to mean this is an estimated or predicted y variable equal to an estimated slope plus an estimated intercept times the independent variable. And this should have a plus EI, these being the residuals. There's still, oh, sorry, the estimated or predicted value does not have the residuals. If you got rid of this hat, just YI would also have the residuals added on here. So this actually, this is correct. You don't have to add on the EI. But they do exist as part of the relationship between the observed X and observed Y. You should add on to here, though, the subscript onto I. So One way to estimate, there are multiple ways to estimate the slope and intercept. One is the method of least squares, where for any given intercept and slope, you can draw a regression line as you see here and calculate each of your observed residuals given that particular value of the slope and the intercept. And the least squares would be the sum of the squares of the residuals, or the squares refers to the squares of the residuals, and the least squares line is the line that minimizes them. And that is the estimated regression line that SPSS or any other software is going to give you. And this is the so-called unbiased estimator of the population values of the slope and intercept. Does anyone want to take a guess as to what I mean by unbiased in this instance? So we estimate a slope and intercept using this method of least squares, and I tell you that the slope and intercept are unbiased estimators of the slope and intercept in the population. Yes.
It hasn't been adjusted for. If you add other variables into the model, you can call it bias.
No, so it doesn't refer to adjusting for other variables. It refers to the fact that if you take repeated samples, so you take many samples, your average values of the slope and estimate of the slope and intercept would converge to what they are in the population. And also, if you took a larger and larger sample, this estimate would converge to what the correct value of the population is. It just means that on average, it's not too high and it's not too low. On average, it's correct. So B0, to interpret it, it is the estimated average value of y when your value of x is 0, and B1 is how much y changes as a result of a 1 unit change in x. So both of these are dependent on the scale of x and y. If you change from kilograms to grams or pounds, both of these are going to change. And well, the B0 is dependent only on the scale of y, B1 is dependent on the scale of both. I showed you that scatter plot early on with the horizontal dashed line and the sloped solid line as an introduction to this idea of breaking up your variation into two parts. So our total sum of squares variation, this is, if you take y bar, that was the horizontal just mean of y line. And these are residuals for between the observed values of y and that horizontal line, a so-called intercept only model. And we can break this up into two components. The first part, the sum of squares of the error. This is also called unexplained variation, and the sum of squares of the regression, which is the explained variation. So the sum of squares of the error are the residuals. These are the observed values of y minus the predicted values of y, the predicted values being from our linear regression, from that line with a slope. So this is the sum of squares of your residuals, or your error terms, your E sub I. And this is the sum of squares of your regression. So these are the mean values minus the mean under the intercept only value. So these are predicted under the linear regression model, the y-hat, and these are predicted under the intercept only model. I'm using y bar to mean the overall mean of y and y-hat to mean the predicted values of y at each value of x. So does this make sense, this breaking up the variation into two parts? Do you remember which one of these is the explained and which is the unexplained part? Just letting you know I'm still watching for questions online. Okay, my question was, do you remember which of these, SSE or SSR, which one is the explained component, which is the unexplained component of your variation in y? So in a regression, we have a y variable that changes. What's one of the examples? The examples that we had, some activity of immune cells, and a predictor variable that is the byproduct of a water treatment. And if we observe a bunch of immune cells, we see some variability in the activity. If we fit a regression model, we'll be able to explain some of that activity using variation in the drinking water treatment byproduct, the treatment byproduct, and some of it will still be unexplained. Which is which in this equation? We have a 50-50 chance. Who thinks that?
Can we use a simpler example? That the water treatment example.
Okay, it's too complicated. Okay, let's say we're explaining test scores by how many hours the student studied. Okay, so we'll see a certain amount of variability in test scores, potentially between 0 and 100. And we also see a certain amount of variability in the number of hours studied. So some of that variability in test scores we'll be able to explain by number of hours studied, but some of it we won't. So which is which here? Sum of squares of total, this is everyone's score minus the overall mean test score. That's what the total sum of squares is. So who thinks this first part, SSE, is the component that is explained by how much you studied? One. How about the other way? Who thinks sum of squares of errors is the amount that's not explained by how much you studied? Okay, see more hands going up. That's right. These are your residuals. These are the test scores minus the predicted test score based on how much you studied. So this is what is not explained by the linear regression. And this part is what is explained. This calculation would be for every student, what you predicted the test score to be minus the overall mean test score. So this is predictions of the model minus the overall mean. So this is entirely the predicted component of the variation. And this is the SSE is the unpredicted component. This is a fairly fundamental equation here in that this is the basis for analysis of variance as well as for correlations. breaking up your total variation into explained and residual or error components. Yes?
Y bar is the average value of Y for all values of X.
Yeah.
Correct.
Yeah, overall average of the overall average for Y. And Y hat are the predicted values from your linear regression. Okay, so our total sum of squares, just to review this because it's important, it measures the variation of Y around the overall mean. This should be Y bar. Let's see. Around their mean Y bar. The sum of squares of error is the variation attributable to factors other than the relationship between X and Y. And the regression sum of squares is the amount of variation in Y that is attributable to variation in X. And the so-called coefficient of determination, or R squared, something you'll hear about many times. If you're not familiar with it yet, you'll start seeing it reported all the time now that you know what it means, is simply the ratio of the sum of squares of regression divided by the sum of squares total. So it's the explained component of the variation divided by the total variation. And it is often described as being the fraction of variation in Y that is explained by variation in X. And that's an okay intuitive way to understand it, but the formal definition of it is from that breakdown that I showed on the previous page. And this varies only between 0 and 1, because sum of squares are always positive, and at bare minimum, if you have a slope of 0, it will be 0, and if you have all of the variation in Y explained by variation in X, it will be 1.
So you don't get R squared by squaring P or R.
Well, in fact, you can. They are related this way, and you outran me by 1 slide. R squared is equal to the square of the Pearson correlation coefficient. Even though they're calculated in different ways, they are equivalent in this way, with the difference that the square root of R squared might be R, or it might be the negative of R, because R can be negative. In the case of a simple linear regression like this equivalent exists, but once you get into multiple linear regressions, there's no such thing as a Pearson's correlation for multiple linear regressions. There's also no such thing as a Pearson's correlation for regressions where you have categorical variables, whereas the big R squared is defined in all of those cases. So big R squared is more generic and widely applicable than Pearson's product moment correlation. But in a case where you can calculate Pearson's R, you can square it and have the coefficient of determination. R squared equals 1 looks the same as when R equals 1 or negative 1. And values in between 0 and 1, again, it can be a positive or a negative correlation, and it means that somewhere between none and all of the variation in Y is explained by variation in X. R squared of 0, Here you notice, thinking back to that equation, how it was the sum of squares of the regression divided by the sum of squares of total. The sum of squares for the regression here is 0 because the predicted values from the regression and the overall mean are the same in every case. So we have a 0 on the numerator. Whereas in this case, the sum of squares of the errors is 0. So the sum of squares of the regression is equal to the total sum of squares, and that's why R squared is 1. These are the assumptions involved in linear regression. First of all, that the population relationship is linear. We have this assumption of homoscedasticity, which means that the standard deviation of those errors are the same across values of x. So you don't have a situation where the residuals are all small on the left side of the scatter plot and they get larger as they go to the right-hand side of the scatter plot. Approximate normality, that for a given x, y is approximately normally distributed. And you'll note this is somewhat different from just saying that, that y is normally distributed or x is normally distributed. X doesn't have to be normally distributed, y doesn't have to be normally distributed. But for a given x, y is normally distributed. Or another way of saying this is that the errors are normally distributed. You can imagine that if you take a bunch of errors and then you add some linear regression line to them, it might not any longer be normally distributed, but it's the error term that is normal. And finally, independence, that we have that all of our pairs of observations, x, y, are independent observations. So if it is relationships between amount of studying and test scores, that each of those observations is from a different student. We don't have, in some cases, 2 different tests for the same student. They're independent observations. All of these assumptions have a compact representation. If we just write out the regression equation with this about the error terms. So the beta 1x, this tells us that the true association in the population between x and y is linear. And this, it is actually also common to write d above this tilde. And this means that the errors are normally distributed with mean 0, standard deviations sigma, and they are independent and identically distributed. The 0 means that for all values of x, the mean is 0. So that is part of the linearity assumption, that we're not consistently over or under predicting for different values of x. And the sigma is the homoscedasticity assumption, that the variance of epsilon is constant regardless of the values of x and y. So again, the assumption of normality is on the residuals, not on x or y. And that distinction is actually especially important when you start doing regressions where you have a categorical predictor, because this can be true that the epsilons are normally distributed, but you could have a bimodal y if you have a predictor that has a binary predictor that has a strong impact on your continuous variable y. If you're just looking at y, you see something binary with small values for, let's say, we're talking about the heights of adults, and it's a mixture of men and women. sex is a predictor of height, and so you might see something that looks like a bimodal distribution before you include sex as a predictor of height. So that's an example of where the residuals would be normally distributed, but Y is not. The coefficients of linear regression are also linked to Pearson's correlation, and they're linked just by the ratio of the standard deviations of those two variables. So if you take your Pearson correlation and multiply by the ratio of standard deviation of Y divided by the standard deviation of X, you get your correlation coefficient. And if they both have the same variance, then your correlation coefficient is equal to the Pearson's correlation coefficient. So you can also think of Pearson's correlation in the example of test scores and hours studying. The slope of your linear regression would be the amount that 1 hour of studying affects the average test score. If you were to standardize hours of studying and test scores by dividing by their standard deviations, so they both have the same standard deviation, then you would interpret your coefficient as being the number of standard deviations in test scores that one standard deviation of increased studying causes, and that would be equivalent to Pearson's correlation coefficient. The hypothesis tests, the results of them are identical, whether you're doing a hypothesis test on your linear regression or on your Pearson's correlation coefficient, because they just differ by that constant factor. Either way. It's getting kind of late and I want to continue on to onto the lab, but let's just do this one example here from the textbook. Body measurements part 4, the scatter plot and least squares summary below show the relationship between weight in kilograms and height in centimeters of 507 physically active individuals. And looking at this scatter plot, it looks like there is a positive correlation between them. That's a lousy regression line. But an increase in height is correlated to an increase in weight. So describe the relationship between height and weight. Let's hear some descriptions. Just shout them out. Positive correlation. Yep.
Strong.
Strong. Yep. Fairly strong. Looks more or less linear. Yeah. Okay, B, write the equation of the regression line. Interpret the slope and intercept in context. So, this is a little hard for me to write here, but let's put weight equals minus 105 minus 105, and this is kilograms plus one. Let's just put 1. It's actually 1.016, and this is
That's the estimated like y-intercept. Like for an individual theoretically who was 1 centimeter tall, they would weigh negative 105 pounds. I'm saying I know that's not really
100 kilograms. Yeah,
like that's where you'd see the line continue.
Yeah, if you had
the y-intercept.
if you extrapolated to a 0 centimeter tall individual, they would weigh minus 105 kilograms,
Okay.
according to this equation. Times height. So there's our regression line. So the slope is not very meaningful. It's an extrapolation to a height that doesn't exist.
And why is the height 1 instead of 0 there?
Why is the height 1 here?
Yeah,
Because the estimate is 1.0176.
that's the estimate of where the y-intercept is. So is it, well, the y-intercept is at 0 on the x-axis, right?
No, the y-intercept is at minus 105 kilograms.
Right, but that corresponds to that's where the line would hit the y-axis.
Yeah, at a height of 0 centimeters. So it means, I mean, there's going to be some non-linearity as you get down to children and infants.
Okay. I'm just trying to picture it like on the graph, because I mean by definition the y-intercept occurs where x is 0, right?
Mhm.
So
here this is x is 150, so 0 is going to be somewhere way over here. So you would have to continue this line all the way. Can't draw very straight, but it would be somewhere way down here. So yeah, let's not put too much. This is one of many examples where the intercept is not something of interest. What's of interest here is the slope, our estimate of the effect of height on weight. And this tells us that on average, for 1 centimeter increase in height, there's a 1 kilogram increase in weight. That's kind of handy. Did the data provide strong evidence that an increase in height is associated with an increase in weight? Well, the p-values here, the p-value is 0, so yes, it does. State a null and alternative hypothesis. Okay, we won't go through all of this, but the null hypothesis is that there is no relationship between height and weight. The correlation here is 0.72. Calculate r squared. It's going to be 0.72 squared, which is going to be around 0.5. And our interpretation would be that about half of the variation in weight can be explained by variations in height. But even for people of a fixed height, there's still about half of the overall variation occurs not explained by height. Okay, so just to wrap up quickly, we're talking about a continuous outcome and a continuous predictor. Pearson's correlation describes both the strength and the direction of that association, and the R-squared coefficient of determination is only a measure of the strength of the correlation. The Pearson's correlation is related, is related to the regression coefficient just by the ratio of the standard deviations. Are there any questions before we'll take a 5-minute break, and then we'll watch Virtual Tony. All right. Thanks everyone online. If there are no questions, I'm going to stop the stream, and then we're going to just put up on the screen here or watch the lab session.
On computer.